First, let's discuss how a Taylor and Maclaurin series, the specific case of the Maclaurin series, can be useful, and then kind of explain its definition and some of its limitations, and how we can tell if the Taylor series sums can be actual approximations. The Taylor and Maclaurin series try to represent a function as infinite polynomials to make it easier to discuss their accuracy and to represent them locally. So let's first define what a Taylor series is. Suppose a function f can be represented by a power series centered at a. This is the first function that is represented at the top here in blue. Our goal is then to find out what the coefficients c0, c1, c2, and so on must be. And we can do this by differentiating repeatedly. As shown here, if we plug in x equals a into the function, we can therefore determine what c0 is when x is equal to a. We can differentiate again, find f prime of x, and then find out what c2 is, and so on and so forth, if we want to find out what those coefficients are. However, this is incredibly tedious, and we would not want to do this over time. We can actually plug in f equals a infinitely in order to find this. But then if we keep going, we can recognize the pattern that is shown at the bottom here in the green function 2, which is that each coefficient solution can be rearranged to show for instance, c2 is equal to f prime of a divided by 2 factorial. If that is understood, then we can notice a pattern that for each coefficient c, we have the following formula to represent it. Therefore, we don't have to differentiate endlessly and can use this to find out what the coefficient is. Combining 1 and 2 from the last slide, here it is again, we can actually give us what a Taylor series for function f centered at a is. F to the n represents the nth derivative at a. X minus a to the n is the distance from the center of the function, and the non-discrimination factor is simply n factorial. What's important to know about the Taylor series here is that this is simply an approximation of an infinite function. Therefore, there's always going to be a gap between what we see here and the actual function itself. But there are ways for us to bridge the gap between that. In order to do that, we need a condition that tells us whether the series represents the function properly, and this is called the remainder term. In this second step, we have a nth degree Taylor polynomial as shown here. And this can be rewritten as a function of x, which is the sum of the Taylor polynomials plus some remainder term. As you can probably imagine, if the limit as n approaches infinity of the remainder is equal to 0, then the function actually is equal to the sum of its Taylor series and is somewhat accurate. Another important note is that a Taylor series does not always work everywhere. You must actually check where it converges. The key idea is that there exists a radius r such that it converges for the absolute value of x minus a is less than that number r, and that if it doesn't, then it diverges otherwise. Finally, below, I've attached some key Taylor series that you should memorize when doing practice problems.
Okay, so in this part, we're going to be talking about the Maclaurin series. A Maclaurin series is a Taylor series centered at 0. It is the simplest and most commonly used case. The core idea is any smooth function can be written as an infinite polynomial where each coefficient is determined by the function's derivative at x equals 0, as you can see below. Now, why does this work? Suppose you want to build a polynomial p of x that perfectly mimics f of x near x equals 0. You need p of 0 equals f of 0. That controls a constant term. Now, p prime of 0 equals f prime of 0. That's going to control the linear term. And p second derivative of 0 equals f second derivative of 0, which controls a quadratic term. And so on for every order. Now, when you differentiate x power to the n exactly n times, you get n factorial. So dividing each coefficient by n factorial is what cancels that out, ensuring that the nth derivative of your polynomial matches f at 0 exactly. Now, what's the core problem? A Maclaurin series is an infinite sum. Infinite sums do not always behave like finite ones. They can diverge, oscillate, or blow up entirely. The central question is simple. For which values of x does the infinite sum actually settle on a finite number? This is where we test for the radius of convergence. The radius of convergence r answers that question. It defines a symmetrical interval minus r to r around the center where the series converges and outside where it diverges. A simple test for that is the ratio test. So you start with a series, and then you compute the limit, which is going to give you the limit on the right. And if L is inferior to 1, it converges. If L is superior to 1, it diverges. And if L equals 1, it is inconclusive, and you have to test endpoints separately. After you found L, you have to check endpoints into the original series to determine if it's an open or closed bracket. Now, if you use a series outside its radius of convergence, the partial sums never settle on number. You get nonsense, and there is no warning sign unless you check first. This is why the radius of convergences tells you how far from the center x0 you can stretch before the series breaks. Everything else is just mechanics. Here you can see some common Maclaurin series. For example, 1 over 1 minus x, 1 over 1 plus x, exponential x, sine of x, cosine of x. But why you need to recognize these? It saves you time and lets you solve most problems instantly instead of rederiving everything. So if you want, you can pause it and screenshot this part. But in theory, you could use the Maclaurin formula. But in practice, taking many derivatives is pretty slow and it could be error prone. And exams are time, so you will run out of time. So I would personally recommend just at least knowing how to recognize these forms of Maclaurin series so that it saves you time and you're just more acquainted with them. To summarize, Maclaurin series are power series, expansions of function center at x equals 0. And in practice, you don't compute them from derivatives every time. Instead, you can recognize a small set of core series and use them as building blocks. Each series has a radius of convergence, usually found using the ratio test, and it requires checking endpoints separately to determine the full interval. The key idea is that most problems reduce to recognizing these standard forms and manipulating them, which makes solving intervals, approximations, and convergence questions much faster and much more efficient.
We talked about the Maclaurin series, so now we're gonna go through an example of it, which is the Maclaurin series for e to the x. So we set f of x equal to e to the x. We know that the derivative of e to the x is always gonna be equal to e to the x. So every derivative is still going to be equal to e to the x. That means that if we set x to equal to 0, f of 0 is going to be equal to e to the 0, which is 1. First derivative of f 0 is going to be equal to 1. Second derivative is going to still be equal to 1. Third derivative still going to be equal to 1, and so on. No matter how far we go, every derivative will still be e to the x, which in this case is equal to 1. So all the derivatives are have the same value. Therefore, what are we going to get from this? Okay, so we know that all the derivatives are going to be equal to 1. So e to the x is actually equal to the sum from n equals 0 to infinite of x to the n over n factorial, which is going to be equal to 1 plus x squared over 2 factorial plus x cubed over 3 factorial, etc. It's going to keep going because of the derivatives are going to be equal to each other. We also found out from our Maclaurin series that the radius of converge is infinite. And what does that mean? If we have the radius of converge being infinite, that means that the series converges for all real x. Series converges for all real x. And this is a great example of the Maclaurin series, and it's one of the most important applications of the Maclaurin series.
So now let's do an example question. In this question, we're finding the Taylor series for the natural log of x centered at x equals 1. So we'll start by writing out the Taylor series formula. Our series is centered at x equals 1, meaning a is equal to 1, so we can just substitute this into the formula. Now we can compute the derivatives of the natural log of x. Now we can evaluate each derivative at x equals 1. Now we can substitute these values back into the formula. Then you just simplify each term, and this is the Taylor series. You can also write this as a summation, which shows the general pattern.